Saskatchewan, that does we design and build these water treatment systems, water and wastewater treatment systems for small to mid-sized communities. So just as a note, my presentation will be from that lens of small to medium size. You could use the same technologies for large plants and large for like a city, but then some of the considerations might be a bit different. But yeah, I'm based out of Vancouver, Canada, and I'm originally from Egypt. Across the world, it's interesting to see how different people, how we target the water treatment across the world. But anyway, so this is going to be our agenda for today. So I know a lot of you or all of you would probably have a good background on source waters, but we'll make sure everybody's on the same page of where our water comes from, because that will factor into what we use for treatment selection factors, and then we'll cover the main bulk of the presentation on membrane technologies, focused on three main ones, RONF, UF, and hollow fiber nano. We'll talk about the theory of how they work, their applications, and when to use them. And then we'll talk also about their operations and some of the things that will be considered here when operating systems like this. And then I'll aim for this to be around 40 minutes so we can have some time for questions after. But that being said, if you want to unmute and ask me partway through the presentation, please, I welcome it. It's better to do this while we're still talking about the slide. So please interrupt me if you have a question. So, very broadly speaking, most of the water that we use globally comes through surface water or groundwater, and some communities also use atmospheric or rainwater. Surface water, as the name suggests, comes from lakes and rivers, and the contamination that's affects surface water is usually very human-made. So things like agricultural, mining, and other industrial applications are what seeps into the surface waters. Also, it's very dependent on weather and climate fluctuations. So different seasons of the year will get different contamination levels. And what happens that you often see that they're high in turbidity, as a lot of you might know, but they don't have a large amount of dissolved minerals. Again, this is a big generalization. Obviously, if you're next to some mining activity or other industrial activity, you can have some of those dissolved minerals. But it's pretty characteristic that this surface water sources would vary seasonally, and like in places like Canada, snow melt and rainfall makes a big difference in surface water quality. On the other hand, groundwater is water under the ground, obviously, and I am not a geological engineer, so we're not going to go too deep into this. You folks might know more about this than I do, but there's different types of groundwater depending on where you're tapping into it. And there's all groundwater is basically water between porous media in the ground. If it's close to the surface or kind of between the water table, it's called an unconfined aquifer. And if it's under the water table, it's a confined aquifer. Water in a confined aquifer is usually cleaner than an unconfined. And you can have two wells kind of right side by side, but depending on which aquifer they're tied into, they could have drastically different water qualities. And these aquifers could be from like a couple of hectares to thousands of kilometers long. They could span very, very large areas, and they're the same aquifer. And usually, so what happens is it's pretty cool. Groundwater gets recharged obviously from surface water, but as it goes through the soil, it gets kind of naturally filtered out. And one of the technologies that I'm sure many of you are familiar with is sand or media filtration that removes turbidity and other suspended particles in water, and that gets naturally treated as that happens too with naturally through the groundwater regeneration cycle. However, as the water moves through the ground, it also has the opportunity to attract or dissolve minerals that are in the water itself. So we see also some generalized characteristics of groundwater where it's low in turbidity because it got captured by the soil, but a high in dissolved constituents like metals and minerals and things like that. Now, the other thing that is important to talk about is groundwater under the influence. So in Canada, here we call it under the direct influence of surface water, GUDI, or at risk of pathogens. In the US, the EPA calls it groundwater under direct influence of surface water. So same thing. But that's usually if it's an unconfined aquifer, where there is a greater risk of pathogens or microbes in the water here, and that gets treated a little bit differently because you get the same risks as surface water, even though you're pulling it from a well. Now, obviously, like that, it's characterized as that if there's significant occurrences of these things here, but also if you see that the water is changing temperature or turbidity or other factors, as groundwater is supposed to be pretty steady and pretty stable because again, it's in those aquifers, you year round you should get the same temperature, maybe a few fluctuations, degree fluctuations here and there, but if you're seeing the fluctuations that you'd see in a lake, then that could mean that it's under the influence, and then you'd need to be much more careful with your disinfection processes. But overall, quick summary, this is more when you're looking at new water sources, and obviously some communities and some places don't have options, but if you are looking at between surface and groundwater, surface water is obviously easily located and accessible. Fun fact, globally, there's a lot more groundwater than surface water. There's about 70% groundwater to 30% fresh surface water. But we, over in Canada and around the world, primarily use surface water because of that ease of accessibility. And you don't need to go digging and finding wells. Also, you can get more data on quality and quantity as well. But the disadvantages, as we talked about, it is more easily polluted and it fluctuates quite heavily during seasons. So oftentimes you have to design for the worst case scenario, but it might be 2 or 3 months in the year that it's seeing these high levels. And this is something that I'm sure folks in the Caribbean are familiar with, but high demand times are usually the driest times. When like the higher the heat, the more the usage. But this also means lower water quality versus groundwater. It is more reliable. You don't get losses through evaporation. If you're withdrawing at a steady rate, you're not gonna the groundwater gets replenished through the water table or the water cycle. Now I have a note here that says it's relatively cleaner, but with a huge asterisk, just because of like again, it does depend on what's in the soil. If you have like a lot of industrial or a lot of agricultural areas around that uses fertilizer, that gets seeped into the groundwater, so it's not always easier to clean. But you can develop it where you need to versus having to build a plant next to a river or a lake or transport water. Usually the aquifers are fairly large and you could put them where you need to. But again, you still have to dig down and find the well. And then you need to make sure that if you're close to the ocean, that it's not salt or brackish water. And you can still deplete an aquifer if you're taking out more quickly, more than what's being replenished. Wells can dry up as people are familiar. Now, yeah, pretty basic. So we have these two main water quality sources, and what we aim to do is to make sure first and foremost that they're free from pathogenic agents that cause disease, but we also want it to be free from harmful chemicals. And the third and fourth ones, the lower priorities, but still to consider, is things that are aesthetically pleasing, addressing taste, smell, and color, as well as making sure it's usable for domestic purposes. Now, this purpose of presentation is specifically membrane technologies. I'm not going to touch upon every technology out there, but that's something that we can talk about in future presentations. But this is kind of a pretty standard diagram that you see often about different treatment methods. So here I'm going to talk about reverse osmosis, nanofiltration, and ultrafiltration, not really micro. Particle filtration is just sand or other media filtration. But all of these membrane technologies work primarily on just a physical separation. You have a membrane with a small pore size, and as you go down this way, you get smaller or larger pore sizes that allow more things through. So reverse osmosis membranes take out most things across the board, and then as you go down, they take out less and less things here. Now, here are the three membrane types that I will go over. The first one is they're called spiral wound membranes, which is what reverse osmosis and nanofiltration membranes fall under. And they're primarily used for groundwater, but they can also be used for surface water application. And I'll dig deep into why here. And then the second category is hollow fiber membranes, which kind of look like this, and they are primarily used for surface water. And then we'll quickly touch upon this is a newer technology called hollow fiber nanofiltration, which combines these two technologies. And I'll spend not a ton of time, but a little bit of time talking about it near the end. Of note, I'm not gonna go through these membrane types just for time, and they're not very heavily used in drinking water. So things like plate and frame modules or flat sheet membranes, more in wastewater. Tubular and capillary modules are also not used very often here. So I'm gonna just focus on these three. Okay, am I going too quick? Things are everybody following along okay?
So far, at least for me, I think that's going good. That's fine.
Okay, fantastic. Okay, so there's two ways that a membrane system works depending on the type of membrane. The first is called dead end filtration, which is kind of what we think about when we think of filtration. You have a membrane surface, you push water through one side, it traps the contaminants, the things that you don't want, and the permeate or filtrate goes through the other side. So that means that all water entering the system is forced out, and like yeah, like nothing, not like there's no wasted water. But this can cause rapid membrane fouling because you're building up stuff on the surface here. Now, alternatively, you have something called a cross-flow filtration method, where instead of pushing the water into the membrane, you flow the water over the surface of the membrane. So what happens as you're flowing the water through, some of it permeates through the membrane while the rest of it keeps going with the contaminants. And what happens that it goes through multiple membrane stages and multiple membrane elements, and each element and each layer keeps getting more and more water through. The advantage of this is that you don't have as much fouling and you have a shearing force that happens as the water flows over the membrane. It cleans itself. But the problem is that with this, you get a continuous waste stream because at the end of the day, not all of the water that keeps flowing through gets removed. So there is a continuous waste stream in this type of technology. And this is how spiral wound membranes work. And then they keep salts in solution instead of pulling them out. So you have less fouling on the surface of the membrane. And this is the first technology I'll talk about, the spiral wound membrane, which again, it's reverse osmosis and nanofiltration. Now, reverse osmosis and nanofiltration, I group them together because there is no hard line about what is considered reverse osmosis versus what's considered nanofiltration. Reverse osmosis is just a tighter membrane, and nanofiltration is a looser membrane using the same technology. And I'll go over that in a couple of slides. So first, what is osmosis? So as some or all of you probably know, if you put like two chambers of water, one with a lot of minerals or salt water, for example, and fresh water with a semi-permeable membrane in between, water wants to flow from the area with less molecules to the area with more molecules to kind of to balance it out. And there's that natural driving force or osmotic pressure that happens that causes this equalization. And interestingly enough, our cells in our body do that quite a lot too, to make sure that our systems are balanced. Now, in reverse osmosis, as the name suggests, you're reversing that flow. So you're applying pressure on this side of the chamber so that you're forcing the water to go through the other way through that semi-permeable membrane. So you need to have enough force to overcome obviously the gravity, but also that natural osmotic pressure that's trying to get water to flow from one end to the other. So this is kind of how it looks like. Like interestingly, obviously the volume doesn't matter if you run this experiment in like beakers or jars, you'll get a higher volume on one side than the other as the water tries to balance it out. But obviously, like if you don't apply the pressure here, the water is going to flow back naturally into this more concentrated area. And it kind of hints at kind of one of the kind of challenges with reverse osmosis that I'll talk about in a second. So here's what a membrane looks like. They're flat sheets of membrane with spacers and and wraps that are like layered on top of each other and then coiled around a central tube. So what happens is that water flows, as I said, it flows perpendicularly, or sorry, flows parallel to the membrane surface, and then it filters, some of it gets filtered through. And what happens, it keeps filtering inwards towards that central tube. So you have the permeate, which is the clean water, and you have the concentrate, which is the waste stream. And for an RO or a nanofiltration system, you can expect to get a recovery of 75 to 90% because of, again, that continuous waste stream. You can push it up, and like there are applications where they push it up to like 95% recovery. But one thing to note is that when it's at 75% recovery, sure, like you're taking 25% and you're wasting it or you're pushing it back to the environment, but that is easier to deal with depending on the regulator than if it's at 90 or 95%, where that 5% is less volume, but it's very, very heavily concentrated. So when looking at designing or operating these types of systems, that's a good consideration to have. But obviously, if you have in an area with water scarcity, or you need to conserve water, you can push the recovery higher. And you do that again by putting more membranes or membrane stages after each other to capture more and more water. Now, obviously, but that is limited by the water chemistry as well. So it's not just about adding more membranes to get the recovery. Sometimes you have limitations just based on your water quality. But this technology, or this process, very, very small pore sizes, removes down to ions. It's in the Dalton range of sizes, very, very, very small. So it removes most things out of the water. And as I mentioned before, the reverse osmosis is just with very tight membranes, and nanofiltration utilizes the same exact process but has looser membranes or with ones with wider pores. And again, different membrane manufacturers would draw the line, like what's considered reverse osmosis and nanofiltration differently. So there's a size that means that it's this or that, and it really doesn't matter that much when you're talking. You're just trying to select the membrane that works for your application. But just so you know that these terms, if you see them around. And for example here, if you have an RO membrane, you get really high salt like high salt rejection, 99% plus. And these are the types of membrane that you'd use for desalination plants if you're treating ocean water or seawater. But that is gets quite intense energy wise. But most of it in Canada, we don't really use any desalination plants, and I know it's hard for a lot of places to do so. And we primarily use low energy ROs on well water because it takes the water out and it captures most things outside. Whereas a NF membrane, it will let some of the smaller particles through. But again, operationally, and visibly, it's identical to an RO membrane. Now, one might ask, why in the world would you use an NF membrane if you have an RO membrane? If RO is the same thing, looks the same thing, costs the same, but it captures more. The answer to that, as some know, is that when you have a wider membrane or a looser membrane that you can push more things through, you can also push more water through or more flow through. So you're able to have smaller size plants to get the same amount of water versus if you're using an RO membrane. So that's one. Also, the pressure requirement to push water through a small hole versus a large hole, it's less with an NF membrane. So you get capital cost savings and you get energy savings from pumping. There's also some savings with chemical addition for adjustments that I'll touch upon a bit later. But just overall, because the RO removes everything in the water, you get pretty clean, like quite pure water that needs some minerals. So if you're putting it through a metal pipe, it's going to start taking the metal out of the pipe and corroding it because it's like just pure water versus NF membranes that let some of the stuff through the water is more stable. Well, we'll talk about this in a little bit. But overall, you get benefits. The main benefits of spiral wound membranes is that they remove dissolved compounds without chemical, like conventionally, if you have dissolved compounds and you're using conventional treatment, you need to add coagulants and flocculants, and you need to, you need to adjust the water chemistry a lot, which I know can be quite tough and requires a lot of operator skill. This one is more from a theory perspective, it's more straightforward and produces reliably safe water. And you have standardized elements. This technology has been around for a while. You can get RO membranes and NF membranes from manufacturers in Asia and Europe and all over the place, and they're fairly interchangeable. And their operation is simple. It's a complex system, but the operation is simple because these units are usually quite automated. So they kind of run themselves, but they are more complex systems. So that's one thing to consider is that there's higher energy cost, and if they're running by themselves, great, like not a ton of operator intervention, but troubleshooting gets harder than because they're more complex. And honestly, like this is so I'd only go with a spiral on membrane on RRNF if like as a kind of last resort. Like can we treat it with simpler methods? And if not, let's look at spiral on, especially for groundwater sources. And I'll talk more about chlorine intolerance here in a future slide, but yeah, a lot of them can't handle chlorine, so you'd have to dose it afterwards. And again, here with this, what I was talking about requires post-treatment. Specifically RO membranes, less NF, but RO membranes, because they take everything out, as I said, they create corrosive water. And also, like, if you think about it, like pure water is at a neutral pH, pH 7. But what happens is this pure water reacts with the carbon dioxide in the air and creates carboxylic acid. So you get RO water becomes actually after a very short amount of time gets lower in pH because of that interaction. So it's low pH, it's corrosive, and then it's quite soft as well. So you might need some post-treatment after an RO system. Now, one thing that I've done and can experiment with is if you have a multi-stage system, you have pre-treatment and then you have an RO or an NF, you could push all the water through the pre-treatment, but then split the stream. And you only put maybe like 50 or 70% of the water through the RO, and then 30% it bypasses, and then you blend it at the end. This way you get a blended water quality that still has contaminants below the levels that are required, but it still has some minerals to for that water stability considerations. So you don't get corrode your pipes and things like that. Now, from an operational perspective, there's a few things to watch out for when operating an RO or NF plant. The first ones being fouling, whether that's bio or particle fouling. The other one is scaling, which is so fouling is when things clog up the membrane. Scaling is when there's dissolved constituents in the water that come out and they scale on top of the membrane. And then membrane damage, chlorine is a big one. They react with the polymers of the membrane and degrade them. So first, membrane particle fouling. Uh, just so like fouling and treatment are different. So if you get any solids in an RO membrane, the RO will stop it. It's not going to go through, but it will coat or cover the surface of the membrane. I have the diagram here again of cross-flow filtration. This kind of self-cleaning action works with the dissolved contaminants and like with low suspended solids, very low suspended solids in the water. But if you have high turbidity going directly into an RO, you get really heavy fouling and it just clogs up the pores of the membrane. And because you're using this cross-flow filtration, you just don't get clean water coming out. Usually this happens at the beginning of the RO system. Again, RO systems are in stages and you have multiple membranes in a row and it goes through. So obviously with the raw water, if it has particulate matter or solids, it's going to clog up the first couple of membranes. So that's a sign that you have fouling. And what that happens usually because of improper pretreatment that doesn't remove those non-dissolved constituents. There's also microbial fouling, and that can happen more anywhere throughout the plant or the system, and that's because of biological compounds, bacteria, algae, things like that growing on the surface of the membrane. Usually, when the system is offline, but this happens if there's a contamination somewhere through the system because they need a food source. The existing bacteria in the water get filtered out with the RO. So it shouldn't really happen, but if it happens, there is some like you might need a deep cleaning of the system. I'm not gonna go through all of these, but this is a list of common foulants, a lot of them being kind of metal oxides, And one important thing to note is these RO and NF membranes are very good at treating these metals if they're dissolved. So if they're dissolved in the water, if you have a well that doesn't have access, it's an anaerobic well, it doesn't, there's no air in it, and these contaminants are dissolved, they'll treat them fine, even at a relatively high levels. But as soon as the water comes in contact with air, air oxidizes these metals and pulls them out of solution and gets them to precipitate. And when that happens, they become solids, so they clog up the membranes fairly quickly. And a big one being iron. Iron is pretty detrimental to membranes when it's oxidized. So one thing that, yeah, obviously when if there's iron in the water, we make sure that either it's the water stays in anaerobic conditions, there's no air coming into the system, or we put a pre-treatment before the RO just to reduce the load on this system. And obviously, there's natural organic matter and other materials that could foul this. So with that, you'll often with RO systems, you'll see a pre-filtration, and I can have another whole presentation on pre-filtration options, things like green sand or manganese dioxide media, or we have biofiltration to sand and anthracite things like that to take the load off the RO before it goes through. And like a lot of membrane manufacturers require that the turbidity be below 1 NTU before you put it through an RO membrane. And again, like these are more commonly used in groundwater applications where naturally the turbidity is already quite low and you're trying to remove some of those dissolved constituents. But yeah, the turbidity will foul the membranes very, very quickly. So yeah, and when we design it, and I think a lot of people do that as well, when they design an RO or an NF, they put a cartridge filtration system right on the skid that may be like 1 or 5 microns to just in case whatever's before it fails and to capture some of that. It's obviously cheaper to replace these pre-filters than the RO membranes. Now, on the other hand, scaling occurs, as I said, towards the end of the RO or NF system, and that happens like if you remember, and I'll pull up again the cross flow. So raw water goes through, some clean water permeates, and then that gets just taken to the reservoir, and it keeps on going on this journey, and it goes through another membrane system. And here's an example of a two-stage. You can have a three-stage. So I said the clean water goes out, and then this raw water keeps going through another stage, and you keep collecting more and more. But if you think about it, like this raw water, it keeps losing clean water, so this becomes more and more concentrated. So there comes a point where this becomes saturated or oversaturated, in which case you get some of specifically if you have high hardness, you get things like calcium carbonate precipitating out, and then that would scale and form a layer over the membrane, and that's gets pretty detrimental because that blocks the membrane entirely, and it's basically won't produce any water through it. But how you address scaling is you dose a chemical called antiscalant. And that what that does is that it makes sure that these scale forming compounds, such as calcium carbonate, stay in the water. And you dose it continuously. You don't need a very high dose. It's a very small dose as the water gets treated, and it prevents that formation. But I've had instances where someone unplugs the plug of the anti-scalant pump, and then the membrane gets scaled up fairly quickly. So it's quite important to do so. So yeah, anytime raw water is fed through a membrane, and usually these are proprietary. There's quite a few companies that produce them, but this could be a logistical challenge because with a lot of the other things I'm going to talk about cleaning, there's proprietary and then there's generic chemicals that you could use that are more easily accessible. But with this, you need to get anti-scalant, and there's not just general chemicals that you can buy. But they can be customized depending on exactly what is in the water that would cause the scaling. But yeah, said within a few hours, you could notice buildups as you see here on the surface of the membranes. And they are with this kind of pH dependent, so you might need some tweaking while you're designing the system to make sure that it operates at a maximum amount. But we really haven't had much challenges with pH, like any detrimental challenges to operating membranes. And yeah, you do not want to overdose this. You need a small amount, and that's it. Actually, anti-scalant, a lot of anti-scalant could help with help biological compounds grow. So then you get biofouling. So it does need to be tweaked. And again, all of this stuff gets tweaked with these systems when they're built and when they're started up. But if the water quality changes, more tweaking might need to be done. Speaking of tweaking, here are some of the indicator, like some of the things that you need to watch out for. But yeah, with some systems, I know I've worked on a lot of sand and anthracite systems that are, or slow sand filtrations that are pretty straightforward to operate. But with these systems, you do need a ton of testing and monitoring to make sure that everything's running smoothly. And a lot of it, actually, in the banner here, are automatic sensors that are online. So that makes sure that the RO is on track, that it's where it's supposed to be, and you can easily troubleshoot if there's any issues. And it also tells you when cleaning cycles are required. So some of the things that you need to test, conductivity from every stage and the permeate. You need temperatures at the feed, obviously, and you need pressures all across. So the feed between every stage and the concentrate and the permeate. And obviously you need to see the flows in the permeate and the concentrate. Now I'll talk about what NPF is here in a second. Additional nice to have, if you have a booster pump or and a VFD, it's good to know the speed. And it's also good to get the pH and conductivity per individual vessel. This might be a bit overkill per vessel, but per stage is probably okay. Now, the idea of when I said NPF, stands for normalized permeate flow. So what happens is that these membranes fluctuate in how much flow can go through them depending on the temperature and some water chemistry parameters. So what you want to do is you want to normalize that flow. At startup, it's like, okay, so when we started up, it was at this temperature, and these are the conditions, and this is the flow. And then this calculation, so when you take a flow measurement in the winter or when it's colder, you can normalize it to that starting temperature, and that normalized permeate flow is what you use to make decisions on things. So it references like new conditions, and it accounts for, as I said, fluctuations in these variables. And then you don't have false alarms because, as I said, the flow will naturally fluctuate with these water parameters. But if you normalize it, then it's consistent. And here, other than normalized permeate flow, other things that you want to keep a note of when you're looking at a RO or a nanofiltration system is differential pressure and other normalized factors as well. I need to be mindful of time. Quick note, so when you have a reduction of 10% or greater in an NPF, this is where a cleaning needs to be scheduled. Once you get to 15% or more, then it should be cleaned within 7 days so you could prevent long-term fouling. And just so you know, cleaning, here's what it looks like, but cleaning anywhere from like very frequent cleanings is once a month, which is too much. Usually you want it to be anywhere between 2 to 4 times a year, type of thing. But it is the most effective way to keep the membrane functioning, and you do that to prolong the membrane life. Like I had a client here that didn't do any cleanings, and he was replacing his membranes every 6 months. These are supposed to last 5 years, but he just didn't want to bother with the cleaning process. But it is quite important. Yeah, and like it could even damage the bigger system and kind of not explode, but kind of go out like that. Okay, so I'm gonna try to be a little bit faster because we still need to talk about the other type of membrane technology that we see often, which is ultrafiltration and technically microfiltration. I've crossed it out because we don't really see microfiltration very much in drinking water anymore. It's mostly ultrafiltration. But how it works, like back to these diagrams, this is operates with the dead end filtration mode. So you have all the water that comes in goes out, and you build up on the surface of the membrane. And what it looks like, it's There's different ways to do ultrafiltration, but again, this hollow fiber method, you have basically thousands of these, let's call them spaghetti strands. So imagine a tube with thousands of spaghetti strands that are hollow. Water goes around the those tubes, and then you pressurize it. Feed water goes through out the middle and captures the contaminants on the outside. You can also have what's called an inside in, so water flows in the middle of the tubes, and then it gets captured in the center. The contaminant gets captured in the center, but then that could clog up a little bit more. So usually you see an outside in like it's depicted here. But what this is used for is primarily surface water because this is very good at capturing things that are not dissolved. So if it's a solid, turbidity, suspended particles, very effective at capturing that. And that also has log removal credits, which means that it removes pathogens very effectively, both bacteria and viruses. The pore sizes of most UF technologies is 0.01. So that is smaller than most, as I said, most bacteria and viruses. So extremely effective at removing those things. I say 90% recovery. The last slide I said all the water that comes in goes out, but you have to factor in that this membrane requires backwashing. So if it runs for a certain number of hours, it gets shut off, and then water has to be backwashed. That's why we say 90% recovery. When it's online, it's 100%, but over a course of a day, you do use some water for cleaning. But here, well, this diagram, microfiltration versus ultrafiltration, the membrane modules look very similar. You don't get the same benefits as you do with nanofiltration versus RO, with the pressure savings and all of that. So with ultrafiltration, it's just a smaller micron. So we've at least with Delco, we've not done any microfiltration systems at all because there's just we don't see no benefits with versus the two. They're both low pressure. This removes only bacteria. This removes bacteria and viruses. Now, one thing to note, I've talked about this primarily from being a pressurized system, which looks like this, where the membranes are in those housings, and we feed water gets pushed through, usually actually from the bottom up, and then you get permeate going out this top tube. You can also get them in submerged, and this is where this is more applicable for larger systems. Now, there are companies out there that do nice modular submerged systems. I know Veolia has one that can be used for small applications that I've seen, where you pull, like you have a submerged tank and you kind of pull the membranes off the side. But for the most part, these submerged systems, you have these big basins, and you fill them up, and then you create a vacuum and you pull the water from the basin through the membranes down the bottom, and that's how you treat. Versus with the pressurized one, you're pressurizing and pushing the water through versus sucking it out. And again, this one is more applicable for large plants where you can, because this, like if you need to build 20 of these skids, it becomes very expensive versus starting to build these larger basins. A quick overall overview of this pressurized versus submerged. This gives you a lot of flexibility because you can always increase the pressure if you need to push more water through, or you need to kind of with cleaning and things like that. But here you cannot create more vacuum. You're limited to atmospheric conditions. It's either you have a vacuum or not. This is usually better suited for colder climate. This has different limitations. Yeah, with these submerged systems, you have to build kind of a crane to pull the whole unit out of the basin versus in a pressurized system, you could just take one membrane out. It's easier to work on. So we generally prefer a pressurized system, but both of these are regularly used. This is what the pressurized UF membrane looks like. So if filtrate comes out, and then we'll talk about actually the modes of operation after we talk about contamination. So you saw the slide before with the spiral wound membranes. You can still get some scaling. You still definitely get membrane damage with the specific chemicals, specific chlorine. But the main thing that you're worried about is fouling when it comes to UF membranes. And that's again usually by oxidized metals. that are oxidized minerals or metals that gets pulled out. However, they are much more suitable or able to handle this than a RONF. So it's not as big of a deal as with an RO or NF, and they're more forgiving. And again, then they have cleaning modes that are quite helpful for this. And biofouling is obviously still a concern. This is the same slide as I had before. So what you do or what we've done before is the UF is quite it's more robust than a than an RO. So what we've done is put a UF membrane first for surface water applications that removes the turbidity, the suspended solids, and all that stuff. And then we put an RO or an NF membrane after to remove the dissolved compounds. And this is in the cases where you have really challenging water. However, there is obviously like the RO can handle, I think, sorry, the UF can handle up to about 100 or 150 NTU. If you have even dirtier water than that, you might need to have something like a big strainer or disc filters or conventional treatment before the UF, so that you're not plugging it up too much and you're reducing the hassle of the cleaning cycles. Obviously, that comes with a greater cost, so it becomes a balance of kind of operator ease versus capital cost. And same thing with the UF. It only like it doesn't remove anything that's dissolved. So usually you need to combine it with things like coagulation, flocculation, or activated carbon to remove things. Now, I have disinfectants here. One cool thing to note is because it's so small, you do get log removal credits. So it depends on your jurisdiction. Usually you still need some form of disinfection, but it could count as one step in removing pathogens. So if the regulator requires you to have multiple disinfection steps, like for example, UV and chlorine, you can put this in and only have chlorine, for example, for disinfection, because it could count as one of those steps. And that's because these UF membranes have what's called a integrity check or air testing. So that happens automatically that makes sure that there's no fiber breakages and no pathogens are going through. So this is some of the modes of operation. So obviously you have filtration. There's a call for water. It filters through, and then once there's no need, it goes offline. And then after it goes offline, it could go into a regular backwash or it could go into a chemically enhanced backwash, which means that you're just dosing some cleaning chemicals, and those could be generic or proprietary to help with the backwash. And then it gets followed by an air scour. Or not every manufacturer puts an air scour, but it just helps kind of break some of those particles that have developed on the surface. Because again, with dead end filtration, you do get that buildup of particles on the surface of the membrane, so you do need to break it up. So air scour just helps and it reduces the chemical need. Sometimes this cycle isn't enough, so you need to do what's called a clean in place, which is common also for the other spiral wound membranes, or you shut the plant down, you fill a tank with usually warm or hot water, and add those more intense or stronger chemicals, and then you flush it through the system for a clean. With this, you still testing and monitoring is still important. You do need to do more handheld testing as well, specifically with things like turbidity, to make sure that the system is operating as it needs to be. And again, the fiber integrity check that happens kind of automatically when the system is running, it stops and it does the integrity test, and it will alarm if one of the modules seems to have a fiber leak. The interesting thing is, and I think I have this in a couple of slides. You can plug if there's an issue with one of the fibers, one of the spaghetti strands, you could just plug it and put the module back in. So you probably don't have to replace the whole thing if there's a fiber failure. And I have a video here shortly. Yeah, some of the performance indicators for UF membranes, pressure, transmembrane pressure being a big one, difference between each side of the membrane, temperature and flux. Yeah, it's not a performance indicator, but it is a factor that affects membranes quite a bit. The main thing here is transmembrane pressure, something that you want to look for. Here, same thing, chemical clean. This is the clean in place. So twice a year at a minimum. That's the recommendation by the manufacturer, and we usually don't do less than that. But we also don't try to go over 4 times a year as much as possible. Otherwise, it tells us there's a more systemic issue, and you might need some pre-treatment if you're cleaning that frequently. And then you figure out that you need to clean when this is TC's temperature corrected transmembrane pressure. So when that increases, when the temperature is consistent, something is wrong, or when the transmembrane pressure increases and it doesn't go down with backwashing, then you know that you need a chemical clean. It's very important that operators keep detailed records because it helps kind of guide what cleaning is to be used. You clean with acid, you can clean with caustic. There's a few different methods. So figuring out what has worked in the past gives you an indication of what will work in the future. Because the water quality, depending on what's in the raw water, causes different types of fouling that would be cleaned with different chemicals. And you could use generic or proprietary chemicals here. Um, Now, this one is these UF members could still be damaged by chemicals, but they are more tolerant on average than an RO or an NF membranes. And different, and like if you know that you have, for example, like you're dosing chlorine directly into a well, or you have to dose chlorine before a UF, there are membrane manufacturers that have ones that are more tolerant than others. So there's some room to work with here. Um, yeah, I'm gonna skip over this because we kind of talked about clean place. But yeah, this is what a fiber breakage looks like in a UF module. So once you've identified like if it fails the air integrity test, you pull the module out and you put it into it's called a pinning bath. It's just a clear container and you push water through and you can see here push air through and if there's a fiber leakage, it can be very easily identified visually, and then you could just go find that one and plug it up. The final technology I'm going to go through super quickly because this is a newer technology, but it's called hollow fiber nanofiltration. And if you've been following along with me, these are two different things. But what happens, what they've been able to do is create basically a UF membrane. So these same spaghetti strands in a vessel, but when they're creating the membrane layer, they create a charge on top of it. So it still removes everything that the UF does, turbidity, suspended solids, viruses, and bacteria. But because of that charged surface, it also allows molecules to attract to it via adsorption. And the big one here is that you get removal of dissolved organic carbon in the same kind of in the same technology versus, as I said before this technology, we do ultrafiltration or some other pretreatment followed by RO and NF to get everything that we need to. In certain applications, we could just use one technology. However, it is newer, and thus the membrane elements are a bit more expensive than either a UF or RO and NF system. So the cost is going down as more and more membranes, more and more systems gets installed. And with the other technologies, there's dozens and dozens of manufacturers that do them. But with this one, there's two in Europe, and I think one or two in China that manufacture this type of membrane. So it's a lot more limited. But again, like looks exactly like a UF membrane, just manufactures with a different polymer with a charge on its surface. But this is from a First Nation application here in BC, where you could see that it removes turbidity very well. Removes this one didn't really have suspended solids, and it removes iron as well. But doesn't remove hardness very much because the charge it's negatively charged. It doesn't remove everything in the water still, so it's not the same as a full RO or an NF system, but it gets you, if you have dissolved organic carbon, you can get at least 80% removal, which is the main use of this technology. Yeah, and it's automated, as I said. It's not like it looks very similar to a UF system, but it does use cross flow. Although it's hollow fiber, it uses cross flow filtration rather than dead end. So there's some changes and differences in design when you look at them. But overall, like when you look at kind of the comparison, DOC, TOC removal, You get very obviously very good removal through an RO and NF. You get pretty good through a hollow fiber nano. But here we have it here in yellow because if you're using coagulation with UF or conventional treatment, as you might know, you require chemical dosing, and that's one operator described it to me more of an art than a science, just to get the coagulant dose just right to make sure that it's removed. Versus these are more consistent. Obviously, the turbidity tolerance, all like obviously this is built for turbidity, and this is not built for it at all. But they both of all of those remove turbidity pretty well. Um, yeah, chemical consumption. The hollow fiber nano doesn't use any chemicals versus a coagulated UF, for example, that you have to continuously dose chemicals because again, it does the absorption based on the charge on the membrane layer rather than chemical addition. Just gonna speed pass through this because I am over time. And this technology again is not something that you use very frequently, but you'd use the same, yeah, you use the same integrity testing. Okay, sorry, I am a bit 10 minutes over time, but we still have some time for questions here, if anybody has any.
Yeah, thank you so much, and Andrew. Yes, please, friends, you should have any questions or comments, please shoot at Andrew. Okay, we have, do you still have production during the backwashing of membrane? If yes, what's the um,
Yeah, that's a great question, Ezekiel. So when you're for RO and NF membranes, they don't backwash. They're running continuously. There's a continuous waste stream, and that's the recovery. So if your recovery is 75% is going through, and 25% is wasted. As for a UF membrane, no, you don't get production during the backwash cycle. So the system stops, and then it has to backwash and that's maybe for 10-15 minutes, depending on if you're doing a regular backwash or a chemically enhanced clean. But then yeah, you do have to stop, wash the system, and then come back to filtration.
any others? Not seen any.
Hey, Ignatius, greetings,
Hi, Kevin. Yeah, great.
greetings from South Florida, and great presentation. I was just at the Caribbean Desalination Association conference. If those of you are not aware of it, a great organization. I was there with Operators Without Borders, but just learning more and more about this technology. Ignatius and I were also in a meeting earlier today, CWWA Florida chapter, Caribbean Water and Wastewater Association, and the forever chemicals were brought up. Also,
Mm,
there's PFAS, perfluoroalkyl substances, something to that effect. In the
mhm.
United States, we're seeing many utilities are going to have to go to membrane to treat these substances. Are you seeing that in Canada or any other countries that you may have experience with?
So in Canada, it's pretty funny. We say we don't have a PFAS problem because we haven't tested for PFAS. So, but no, but that's the joke. But it's under review new guidelines for PFAS, and that's a big part of our association's meetings. So we are going to see more and more of that come through. Um, Again, it does obviously it's based on like uh, human uses. They're human-made chemicals, so it depends on where you are. And a lot of our concept population is concentrated towards the south, and you don't get as much contamination in some of the other places. But yeah, it is definitely a concern, and it's very unfortunate because you do need RO or NF membranes to treat for PFAS and these forever chemicals. I know there's some success using activated carbon as well. Um, but I don't have much experience with the activated carbon aspect of it.
Great,
Yeah,
thank
we
you.
have us. Go ahead, Stefan.
Hi, thank you for the presentation. It was very informative. Um, one of my concerns is with dissolved gas. So in
Mm,
situations where you have let's say sulfide or even high carbon dioxide,
yeah.
what um what solutions would you recommend for, I guess, post-production, or could it be eliminated in pre-treatment?
So what we do for degasification usually is done after the membrane systems. And there's different technologies, and I'm not as familiar with them off the top of my head here. So I know they are different, but yeah, these membrane technologies do not address um, carbon dioxide or other gases because they do go through the membrane barrier through the water. But then you do need a separate degasification step. And we could touch base after if you know what exactly is in your concern, and we could look into some options there.
Okay, thank you. The other thing though as well,
Mhm.
um, in terms of adding a little bit of alkalinity, because once it goes through that reverse osmosis membrane,
Mhm.
all alkalinity is virtually gone.
Yeah.
Um, you have any recommendations on those as
Yes.
well?
Yes, so there's a few different ways to add for remineralization after an RO. The thing that I like to use most is called a calcite contactor. So what it is like just a vessel. It could have an FRP steel vessel or whatever, and you fill it with calcite, and you when you push the water through, it slowly the water slowly dissolves some of that calcite, and that adds alkalinity back into the water. And like you do some of the challenges with calcite contactors is pH. You do need to have the right pH, and it's a little bit it's a bit of a small range of pHs that you need so that it could dissolve properly. That's one method. You can also have a chemical pump, and we could dose kind of concentrated solution, although I see that less frequently. And again, the method that we often used to, if possible, is that blending stream. So instead of pushing 100% of the water through the RO, you calculate, okay, like I need to remove arsenic, but arsenic is a bad example because you want to remove all of it. But let's say I want to remove manganese, but if you treat only 50% of the water, you could take the other 50% and the RO and blend it. Your manganese level is still going to be lower than the maximum that you need, but you still keep some of that alkalinity and minerals in the water, in the blended water afterwards. So that method it's quite nice because you actually make the RO system smaller, so you save on cost and operational complexity while solving that problem without having another additional step. Usually, with that blending option, though, you should have a pre-treatment because in some cases you could just have RO directly from a well. You could push into an RO, but if you want to use that blended option, we highly recommend a pre-treatment, both to protect the RO and also as a barrier. So you're not pushing water from a well, for example, directly through to consumers without any filtration steps.
Yeah. But going back to your point on I think arsenic, if you found arsenic in the water,
Mhm.
what sort of measures would you use to get it out?
That's an excellent question. By the way, I do have a full presentation on arsenic. I'm happy to come back and present on it.
Yeah, that would
So
be useful.
yeah, so arsenic, there's a few ways that you could remove arsenic. Uh, it depends on if the arsenic is arsenic 3 or arsenic 5, because one is much more easily removable than the other, even for RO membranes. If I remember correctly, I think it was arsenic 5 that was easier. I always mix the two, but you need to even RO membranes would have a 98% removal of one arsenic and like a 70% removal of the other. The other thing that you could use, though, we've done pretty effectively, is if you oxidize the arsenic again to the more easily treatable form, things like um, green sand or Phylox media have been shown to effectively remove arsenic. Arsenic gets removed better if there's higher degrees of iron in the water. So if you have a high amount of iron, then that media filtration, either with green sand or pyrrolite is another one. Manganese dioxide media could be very effective. If you have low iron, then you'd want to use an RO membrane. We also have there's also a technology that exists out there called biofiltration, where it's biofiltration for groundwater. It's different than what you've seen for wastewater, where you get bacteria that oxidizes iron and manganese. And when they oxidize them, they take them out of solution. And if you have higher iron and the bacteria, the iron oxidizing bacteria, when they oxidize the arsenic co-precipitates out with the iron. So you could use the biofilters without any chemical addition to remove arsenic. But that is a less reliable method than the other two.
I think you have two questions in the chat. Another one
Oh,
from Ezekiel. Do you still have production during the backwashing of the membranes? If yes, what's the difference in production
oh, I
when
believe we
compared to
answered.
normal operations?
I believe we answered those already.
Oh yeah, you did that. Okay. And I think Stefan would like to follow up with you.
Yeah, my email is on the screen. Feel free to send me any questions that you have. I'm on paternity leave for another 2 days, but then I'll be back to checking my emails. So I'm happy to connect.
Yeah. All right. Well, I see no more questions. I would like to thank you so much, Andrew, for taking time off your paternity leave to spend at least this hour with us. And I think it was very informative. I had the opportunity last week to visit one of these massive ultrafiltration systems. And I think, it just brought home a lot of, or reinforced some of what I had learned from that visit. So thank you very much. And we'd like to thank all our participants for the good questions, but especially to you for that wonderful presentation. And I'm Ignatius John, the Executive Director at the Caribbean Water and Sewage Association. This is webinar number 11 of 2026, and we're signing off. Of course, it is being recorded, and we're going to post it on our YouTube site. Thank you very much. Have a good evening, everyone. Bye.
Bye.
Thanks, Ignatius. Thanks, Andrew.